Tonight, if you can't sleep, let us gently explore one of the strangest experiments ever performed in science. There is nothing you need to solve, nothing you need to understand perfectly. Just listen slowly. Let the ideas move quietly through your mind. The experiment we are going to explore is called the double-slit experiment. It sounds simple. Two small openings, a source of tiny particles, and a screen behind them. But this simple setup changed how we understand reality. Before this experiment, scientists believed the universe behaved like a predictable machine. If you throw a ball, it follows a clear path. If you shine light, it travels in straight lines. Everything seemed stable, logical, comforting. But the double-slit experiment revealed something unexpected, something soft and mysterious beneath the surface of what we call reality. Let us imagine the setup slowly. Picture a wall. In this wall, there are two narrow openings. Two thin slits cut into the surface. Behind the wall is a large screen. In front of the wall, scientists place a source of particles. Sometimes they use light. Sometimes they use electrons. Tiny particles that are much smaller than atoms. Now imagine the particles being fired toward the wall, one by one, gently. If these particles behave like tiny solid balls, something simple should happen. Some particles go through the left slit. Some go through the right slit, and on the screen behind we should see two clear lines forming. Two bright bands, one behind each slit. That would make sense. That would match our everyday experience. But that is not what happened. When scientists performed this experiment with light, something surprising appeared. Instead of two clear bands, the screen showed a pattern of many bright and dark lines. A striped pattern. This pattern is called an interference pattern. It looks like overlapping waves, like ripples in water that cross and combine. Where two waves meet, they sometimes strengthen each other. Sometimes they cancel each other out. The result is a series of light and dark bands. This pattern only appears when waves overlap, not when solid particles pass through one path or another. This suggested something strange. Light, which we sometimes think of as particles, was behaving like a wave. But scientists wanted to go deeper, so they repeated the experiment with electrons. Tiny particles of matter. Surely solid matter would behave like tiny balls. Surely electrons would pass through one slit or the other. But once again, the same interference pattern appeared. Bright and dark stripes, as if each electron was somehow passing through both slits at once, as if it were behaving like a wave. Even more strangely, scientists slowed the experiment down. They fired electrons one at a time, not in a stream, but individually. You might expect that one electron would go through one slit, then another would go through one slit, and eventually two simple lines would form. But that is not what happened. Even when electrons were fired one by one, over time the interference pattern still formed, as if each single electron was interfering with itself, as if it somehow traveled through both slits at the same time. This is where the mystery deepens. Let us pause and imagine that. A single particle, not split into two pieces, not duplicated, but somehow behaving like a wave spread out in space, passing through two openings, and then arriving at the screen in a way that creates a pattern, not randomly, but according to wave-like rules. This suggests something profound. Before it is measured, the electron does not behave like a tiny solid dot. It behaves like a cloud of possibility, a wave of probability. a gentle spread of potential locations. Only when it interacts with the screen does one position become visible, and even then, the full pattern emerges only after many electrons have arrived, softly building the striped image over time. This is not how our everyday world works, and yet, at the smallest scale, this appears to be reality. Now imagine yourself watching this experiment in a quiet laboratory. The room is dim. The equipment hums softly. Particles are being released one at a time, each one invisible, each one traveling toward the wall, and slowly, almost magically, a pattern appears on the screen. Not chaotic, not random, but structured, ordered, wave-like. It is as if the universe at its smallest level does not choose a single path immediately. It explores possibilities, it spreads out, it remains open, until interaction forces a decision, and that openness is the heart of the mystery. Let us continue exploring it slowly. Let us continue gently. The interference pattern suggests that something wave-like is happening, but scientists were not satisfied. They wanted to know something very specific. Through which slit does the particle actually pass? Left or right? It seems like a simple question. Surely, even if the particle behaves like a wave, it must go through one opening or the other. So they modified the experiment. They placed tiny detectors near the slits, devices capable of observing which slit the electron passed through. Nothing dramatic, just careful measurement, just observation. And this is where the experiment becomes truly strange. When the detectors were turned on, something changed. The interference pattern disappeared. The striped wave pattern vanished. Instead, two simple bands appeared on the screen. Exactly what we would expect from tiny solid particles. As if the electrons had decided to behave normally. As if they now chose one slit or the other. The only difference was observation. When scientists measured the path, the wave behavior stopped. When they did not measure, the wave behavior returned. It was as if the act of observing changed reality. Not in a mystical way, not in a magical way, but in a physical, measurable way. Measurement altered the outcome. This leads to an important idea in quantum physics. Before measurement, the particle exists in what is called a superposition. Superposition means that the particle does not have one single definite state. Instead, it exists in multiple possible states at once. In the case of the double-slit experiment, the electron exists in a superposition of going through both slits, not choosing left, not choosing right, but remaining open, remaining spread out. Only when measured does this superposition collapse into a single outcome. One slit, one position, one measurable path. Let us slow that down. Imagine a soft cloud. This cloud represents the possible locations of the electron. It is not a sharp point, it is a spread of probability. While the experiment is unobserved, the cloud remains open. It flows through both slits. It interferes with itself. It creates a pattern. But when we measure which slit it goes through, we force the cloud to shrink, to choose, to become definite. The wave collapses into a particle. The possibility becomes a fact, and the interference disappears. This is sometimes called the observer effect. But the word observer can be misleading. It does not mean human consciousness creates reality. It means that interaction creates reality. To observe something at the quantum level, we must interact with it. We must bounce light off it. We must detect it with instruments. And that interaction disturbs the system. It changes the conditions. At the smallest scale, nothing can be observed without influence. Reality is delicate. It cannot be touched without being altered, and that delicacy is part of its beauty. Imagine standing quietly in that laboratory again. The detectors are turned off. The electrons behave like waves. Soft interference patterns form. Now the detectors are turned on. Instantly, the pattern simplifies. Two bands, two paths, certainty. The only change is measurement. It feels almost as if the universe behaves differently when watched, as if possibility narrows into reality under scrutiny. This is not something we see in everyday life. A car does not change its path because we look at it. But at the quantum scale, the rules are different, and the double-slit experiment is one of the clearest demonstrations of that difference. Some interpretations of quantum mechanics suggest that before measurement, the particle truly does not have a definite position. It is not hiding a secret path. It is not secretly choosing left or right. Instead, it genuinely exists in a state of potential, a range of outcomes, a soft openness. Only when interaction occurs does one outcome become real. This idea challenges our intuition. We are used to thinking that objects always have definite properties, even if we do not know them. But the double-slit experiment suggests something deeper. That definiteness itself may arise only when conditions require it. Until then, reality remains flexible, unfixed, and quietly mysterious. Let that idea settle. A universe where, at the smallest scale, things are not solid and predetermined, but fluid and responsive. A universe where possibility precedes certainty, and where observation is not passive, but participatory. We will continue to explore what this means, slowly, gently, without rushing toward conclusions. Let us go deeper into the mystery. Why does observation change the result? To understand this, we must think carefully about what measurement really means. In everyday life, measuring something feels passive. We look at a book, we look at the sky, we look at a chair. Nothing about those objects seems to change simply because we see them. But at the quantum level, seeing is not passive. Seeing requires interaction. To detect an electron, scientists must shine light on it. Light itself is made of particles, called photons. When a photon hits an electron, it transfers energy. It nudges the electron. It disturbs its motion. At large scales, this disturbance is too small to notice. But at the smallest scale, it matters. Even the smallest interaction can change the outcome. Imagine trying to observe a tiny floating speck in total darkness. To see it, you must shine a flashlight. But the beam of light pushes the speck slightly. The very act of seeing changes its position. Now imagine that speck is unimaginably small. So small that any touch alters it completely. This is similar to what happens in the double-slit experiment. Observation is not neutral. It is participation. When detectors are placed near the slits, they interact with the particles. That interaction forces the system into a definite state. The electron can no longer remain in superposition. It can no longer remain a spread of possibilities. The act of measurement collapses the wave into a particle-like behavior. Two slits become two paths. Possibility becomes choice. Wave becomes particle. Some physicists describe this using the concept of the wave function. The wave function is a mathematical description of all possible states of a system. Before measurement, the wave function contains multiple possibilities. It is wide, spread out. When measurement occurs, the wave function collapses. It narrows. Only one outcome remains. This collapse is not something we see directly. It is something we infer from the results. And yet, it appears consistently in experiments, again and again. This idea leads to many interpretations. Some suggest that the particle truly exists in all possible states until measured. Others suggest that reality splits into many branches, where all possibilities occur in parallel universes. Some interpretations avoid collapse entirely and describe the process differently. But all agree on one thing. The double-slit experiment reveals behavior that cannot be explained by classical physics. The universe, at its smallest scale, is not built like a machine. It behaves more like a field of possibilities. Let us imagine once more the quiet laboratory. The slits cut into the wall, the faint glow of detection screens, electrons moving silently through space. When no one measures their path, they act like waves. When measurement is introduced, they act like particles. It is as if reality holds multiple answers, and only when asked a specific question does it give a specific response. Ask, which slit did you pass through? The universe answers with one slit. Ask no question, and the universe responds with waves. Soft interference, open potential. This does not mean that the universe is conscious in a human sense. It does not mean it waits for our thoughts. It simply means that physical systems respond to interaction. At the quantum scale, interaction defines outcome. Without interaction, systems remain in superposition. With interaction, they become definite. This simple distinction reshapes our understanding of reality, not dramatically, but quietly, gently, in a way that invites reflection. Now imagine this principle extended beyond the laboratory. Every object around you is built from quantum particles. Every surface, every atom in your body. At the smallest level, particles exist in soft probability distributions. Yet, at larger scales, stability emerges. Your bed feels solid. The room feels still. The world appears reliable. Out of uncertainty comes structure. Out of probability comes form. And perhaps there is something comforting in that. The deepest layer of reality may be uncertain, but it gives rise to stability. It gives rise to experience. It gives rise to the world you know. And we are only beginning to understand it. Let us step back now, slowly, gently, and imagine what the double-slit experiment might mean for the universe as a whole. If particles behave as waves of possibility until interaction occurs, then at the deepest level, reality is not fixed. It is open. It is responsive. It is shaped by conditions. The smallest building blocks of matter do not follow rigid paths. They explore potential. They exist in superposition. They remain undefined until interaction narrows them into one outcome. This may feel unsettling at first, but let it soften. Let it become gentle. Because uncertainty at the smallest scale does not create chaos. It creates flexibility. It allows structure to emerge in stable ways. Imagine the early universe, long before stars formed, long before galaxies existed. Tiny fluctuations of energy moved through space. Quantum fluctuations. Small differences in probability. These subtle variations may have shaped the large-scale structure of the cosmos. Clusters of galaxies. Vast cosmic webs stretching across unimaginable distances. From the smallest uncertainties came the largest patterns. From quantum waves came stars. From probability came planets. From microscopic softness came the solid ground beneath your feet. The double-slit experiment reminds us that the universe is layered. At one level, it appears predictable. At another level, it is fluid. You live in the stable layer, where objects behave reliably, where gravity pulls downward, where walls do not dissolve into waves. But beneath that layer, at the quantum scale, motion is constant, possibility is constant, superposition is constant, and yet you are safe within the structure it creates. Uncertainty does not threaten stability. It supports it. Think again of the interference pattern, bright and dark stripes forming slowly on a screen. Each electron arrives as a single point, yet together they reveal a wave-like pattern. Individual events, collective structure, tiny actions. Large patterns, this is emergence. From simple rules at small scales come complex structures at large scales, and the double-slit experiment is one of the clearest windows into that hidden process. Now imagine your own body. Every atom inside you behaves according to quantum rules. Electrons exist in probability clouds. Energy levels shift. Particles interact. Yet you feel stable. You feel whole. You feel solid. That solidity is not a contradiction of quantum mechanics. It is the result of countless quantum interactions balancing into stability, a dance so complex and consistent that it appears still. There is something quietly beautiful about this. The world is not built from rigid certainty. It is built from dynamic potential. It is built from relationships, from interactions, from responses. And the double-slit experiment reveals this softness in the simplest possible way. 2 slits, a wall, a screen, and a pattern that should not exist under classical rules. Yet it appears, again and again, reliable in its strangeness. Let your mind rest with that image. 2 narrow openings, a gentle stream of particles, a striped pattern forming slowly in the dark. No rush. No urgency, just quiet evidence that reality is deeper than it first appears. You do not need to resolve the mystery. You do not need to decide what interpretation is correct. You can allow the strangeness to remain. Soft, unfinished, open, just like the particles themselves before measurement. Let the idea of possibility settle in your thoughts. Let certainty loosen. Let definitions soften. There is nothing to prove, nothing to calculate, only quiet patterns forming in the background of existence. And as those patterns fade gently from focus, you can begin to drift. Let us slow everything down now. You have traveled through the mystery of the double-slit experiment. 2 small openings, a silent stream of particles, a screen in the dark, and a pattern that should not exist, yet does. There is no need to understand every detail, no need to remember every term. What matters is the feeling of openness, the sense that beneath the surface of ordinary life, something softer exists, something fluid, something quietly responsive. At the smallest scale, particles do not rush to become definite. They remain possibilities, they remain waves. Only when interaction requires it do they choose a path. And perhaps, in your own life, there is comfort in that idea. Not everything must be decided immediately. Not everything must be fixed. Some things can remain open, unmeasured, uncollapsed, just gently existing as potential. Imagine again the dark laboratory, the faint hum of equipment, electrons traveling invisibly, each one arriving softly at the screen, each one adding to a pattern that slowly becomes visible. No single electron creates the full image, but together, patiently, they form structure. In the same way, your thoughts can slow, one breath at a time, one moment at a time. No urgency, no sharp edges, just gradual formation, gentle settling. The double-slit experiment shows us that reality at its core is not harsh. It is subtle, it is relational, it responds to interaction, it adapts to conditions, and from that softness, stability emerges, from uncertainty, structure, from waves, form, from probability, experience. You are part of that structure, built from the same quantum behavior, yet resting here in solid calm. As you lie there, perhaps in a quiet room, perhaps in the dim light of evening, imagine your thoughts behaving like waves, not sharp, not rigid, just moving gently, overlapping, interfering softly. Some thoughts strengthen, some fade, bright bands and dark bands of awareness, but all part of the same quiet pattern. There is no need to observe them closely, no need to measure them. When you stop measuring, patterns soften. When you stop asking which slit, which answer, which certainty, the wave returns. And maybe sleep is a kind of gentle superposition, a state between clarity and dream, between wakefulness and rest, where thoughts are not forced into definite conclusions, where the mind remains open, floating lightly in probability. You do not need to collapse every thought tonight. You can let them pass through both slits. You can let them remain unresolved. The universe does not rush its particles, and you do not need to rush yourself. Two slits, a wall, a screen, soft particles moving through space, waves overlapping, patterns forming slowly. And in that quiet formation, there is peace. There is something steady, even in uncertainty, even in mystery, especially in mystery. Let your breathing slow now. Inhale gently, exhale softly. Imagine the interference pattern fading into darkness, the stripes dissolving, the screen dimming, the laboratory lights lowering. No more measurement, no more questions, only quiet potential, only calm, only rest. And as the pattern fades, you can drift, slowly, quietly, into sleep.